Hello, good afternoon. I'm Dimitrios Bikiaris, and I'm professor here in Aristotle University of Thessaloniki. I would like to welcome you all to this workshop, to our REDONDO project. Okay, it's an EU project. We are in the third year, 36 month. We close at the end of August. And I can say a few words about the problem that we face here. We need to produce reversible cross-linked polyethylene materials. These materials are used today for many applications, especially for pipes, for hot water drinks, for internal uses. We have a small company, an SMS company from Greece, Interplast, that is producing these pipes for long years, since long years, and is one of the leaders not only in our area, but export these pipes everywhere around the world. And also, the second test case that we have here is for cables for photovoltaics, because we need also their durable materials. All these materials are from cross-linked polyethylene. We have several types of polyethylene, low density, high density, linear low density, and we have also cross-linked polyethylene. This polyethylene is a thermosetting material, a material that cross-links after its production of the pipes or the cables, which is the problem, that these materials, after their uses, cannot be recycled. Are materials that are, as I said, thermosettings and cannot be recycled. So we face a big problem how we will handle all these materials. And in our project here, we have seen different procedure to produce some reverse cross-linked materials. What does it mean? That we will have a cross-linked material during its life application, but after, at higher temperature, these cross-linked bonds will break down and we will produce again a thermoplastic. Except of this, in our project, we have the synthesis of novel green and bio-based additives. This is one challenge to produce such bio-based, and this is also the EU policy the last years to produce some materials to use bioeconomy and bio-based alternatives to displace to all these materials that are used, additives and monomers, and to produce all this from bioresources using biomass. The production of recycled PEX nanocomposites using bio-based additives, nanolignin, nanocellulose, and others. Production at the end with the use of all these materials, some cables and pipes, and the development circularity monitoring tool, placement tool, and establishing safe by design and sustainable by design criteria for reversible cross-linked material. This is also, as I said, in the EU policy. It was changed the last years, and in 2022, EU announced a new policy for all the materials and procedure in order to reduce carbon dioxide emission, to make more safe materials, and to reduce the energy that using for all their production. The concept, as I said before, polyethylene cross-linking affords a material with improved properties. We have a material that can be, for example, in the pipes stable during hot circulation of water and for long time, for 70 years. And this can be achieved only by cross-linking. It is not possible to use high-density polyethylene because it has a melting point around 1040. It will be will become soft during hot water circulation, and that's why we need the cross-linked material. So it has a high thermal stability, important for hot water application, reduction in creep deformation, higher chemical resistance, because we know that water has almost inside chlorine and other additives, improved abrasion resistance, great impact strength, less node sensitivity, and abrasion. All these properties are important for these applications, and this is the reason why the cross-linked polyethylene can be used here. Due to the formation of cross-linked polyethylene are not behave like a thermoplastic. They are thermosettings. This means that cannot be remelted and to produce a new material. After cross-linking is a material that cannot be used again. To solve this problem in a Redondo here, we'll develop reversible cross-linking reaction based on the formation on disulfide bonds. We know that disulfide bonds can be easily break down. It elevates thermocracies, temperatures, and the reversible bonds based on Diaz-Alder reaction. Responsible for the first task is Aristotle University of Thessaloniki, and for the second task is the University of Montpellier with Sylvain Caillol to lead this group there. All these materials will be stable during their use, and we will produce some thermosetting at higher plastics at higher temperature, where these bonds will be claved down. The further scope here is to reinforce all this with appropriate green and bio-based additives and to produce composites with enhanced properties for this application, flame retardance, stability, etc. And as I said, nanolignin and nanocellulose can be used for such applications. We have different phases in our project. Almost some of them have been completed. The first is the safe and sustainable by design material. We have here the study to determine and of the specification that required and associated with the development and reversible cross-linked material and additives, health risk of all additives and the used materials in the final products, of course, reversible cross-linked polyethylene, which is very important with the two cases, disulfide bonds and Diaz-Alder reactions, and the third phase implementations here, sustainable green or bio-based additives to produce bio-based and green additives as nanolignin and nanocellulose, which are the two of the most important nano additives produced from biomass in order to be used and also to functionalize them to enhance the properties and especially the flame retardant properties. And the last validation demonstration activities, which is very important for all projects, not only for Redondo. Master batches will be produced here, and at the end, will produce some products, final products. And the need here is to see that indeed we produce a reversible cross-linked reactions, and all the produced final materials are really reversible, can be melted again and reused. The consortium, we have here 11 partners from 6 different countries. Aristotle University of Thessaloniki, our group, leads this consortium, and we have CNRS with Sylvain Caillol from France. Ceylon is the leader group in Europe producing cross-link polyethylene. Creative Nano from Athens to produce some nano additives. Aymen from Spain in order to produce some new materials. Interplast, as I said, a company from Greece located in Komotini, producing these pipes. KB from Berlin Electronics, producing the cables for the photovoltaic applications. Itene from Spain, AXA Innovation from Germany, RDC from Greece, and ISQ from Portugal. All these are our partners. Several work packages are in our project. The most of them are finished. You can see here the duration, and some of them are finished the next years, where we will have our last meeting for the project. Also, we have different milestones. The most important have been already finished, and we are somewhere here in the 36th month, where after our studies in the lab here in Aristotle University of Thessaloniki and Sina Res, we produce some materials with reversible cross-linked properties, and at the end, Ceylon, which is the leader, as I said, for the production of reversible cross-linked materials, has to produce 10 to some hundred of kilos of these reversible cross-linked materials to give in Interplast and in KBA in order to produce the final material. And after, to see all these materials, if they have the properties that has the original, the neat cross-linked polyethylene without this reversible cross-linked bonds, and to see the reversibility in real time, to melt again all these materials and to make some thermoplastic, and if it is possible, to produce again some pipes or some cables. This is the concept, the whole concept of the project, and I would like to thank you all for being here, and I hope to enjoy all the presentation for our participants.